Hello everybody, I'm Dr. Hecht, and today we're talking about the chemical equilibrium between sulfur dioxide and sulfur trioxide. This picture shows sulfur. Sulfur is an abundant mineral. Refineries produce sulfur in large quantities because they are legally required to remove the sulfur that is extracted with fossil fuels before selling their products, such as gasoline for automobiles. Otherwise, the sulfur in the fuel would be combusted with the fuel to form sulfur dioxide. Sulfur dioxide exists in equilibrium with sulfur trioxide. You can smell these gases when you strike a match. Following the Industrial Revolution, gaseous sulfur emissions became the primary agent causing acid rain. Sulfur dioxide is an air pollutant which is regulated in most countries. In example 3.7, in the textbook Air Pollution and Greenhouse Gases from Zhongchao 10, you were told to consider a mixture of 64 kilograms of sulfur dioxide and 32 kilograms of oxygen mixed with 56 kilograms of inert nitrogen in a sealed reactor. This system comes to equilibrium, and the system has a temperature of 1000 Kelvin and 2 atmospheres of pressure. This is an equilibrium with sulfur trioxide. So the difference between the system on the left and the system on the right is that some of the SO2 and oxygen have reacted to form sulfur trioxide. So the first step when we're talking about reactions is to recognize that when we're looking at this reaction equation, we're not talking about kilograms, so it's not kilograms of sulfur dioxide that react, but it's the basis for our calculation will be in moles. So the first step I want to know is how many moles of each of these gases exist in the container. So sulfur has a molar mass of 32 and oxygen of 16. So SO2, 16 times 2 is 32 plus 32 for the sulfur, gives us a molar mass of 64. So 64 grams per mole. And if I have 64 kilograms, this means with 64 grams per mole, I have 1 kilomole of sulfur dioxide. For oxygen, I have a molar mass of 16. So for this O2 molecule, I would have a molar mass of 32 kilograms, which means I also have 1 kilomole of O2. Nitrogen has a molar mass of 14, meaning for each mole of nitrogen gas, N2 gas, I have 28 grams. I'm told I have 56 kilograms, so this means I have 2 kilomoles of nitrogen. So I have 1 kilomole of SO2, 1 kilomole of oxygen, and 2 kilomoles actually of nitrogen. Okay, now this system reaches equilibrium, and part of my SO2 and O2 have reacted to form SO3 according to this reaction equation. I don't know exactly how much, that's actually what I want to calculate. And so I'm just going to say it's Y. I have some amount Y of SO3 that has been formed by reaction. And because forming SO3 consumes some SO2 and some O2, the amount of SO2 that I have has been reduced by this amount Y. And the amount of O2 that I have has been reduced by Y divided by 2, because I only need a half mole of oxygen for each 1 mole of SO3. And in the container, I still have 2 kilomoles of nitrogen, which has not participated in this system. So when I compare the system on the left and the system on the right, on the left system, in total, I have 1 kilomole of SO2, 1 kilomole of O2, 2 kilomoles of N2 for a total of 4 kilomoles of gas. On the right side, I have Y plus 1 minus Y plus 1 minus Y half plus 2. In total here, it depends on the value of Y, but in total I have 4 minus Y divided by 2 moles of gas. And here, I've summarized this in a table. So before reaction, I have 1 mole of SO2 gas, 1 mole of O2 gas, 2 mole of N2 gas, and in total I have 4 moles. At equilibrium, I have 1 minus Y, 1 minus 0.5 Y, Y, 2, and in total 4 minus 0.5 Y kilomoles of gas. So in the problem, I'm given an equilibrium constant, and I am told that Kp is equal to 1.8. So 1.8, this equilibrium constant I know, is related to this equilibrium reaction. And P is meaning the partial pressure, so this is given in terms of partial pressure. And in the numerator on the top, I will have the partial pressure of the product, SO3, raised to the power of 1 because there's 1 mole here. And in the denominator, I have the reactant, so the partial pressure of SO2 raised to its stoichiometric coefficient, which is 1, and the partial pressure of oxygen raised to its stoichiometric coefficient, which is 1/2. So the partial pressures I don't have, but instead I have these number of moles of substance, which was given to me in the problem that I've summarized in this table. And the partial pressure is the fraction of this gas in the mixture multiplied by the total pressure. So I can rewrite this that the number of moles of SO3 divided by the number of moles total times the overall pressure is equal to the partial pressure of the gas. And I can repeat that for SO2 and for oxygen. Okay, the number of moles of SO3, SO2, and O2, they depend on Y, but they're given here in the table. And so I can separate these three terms and I can pull out pressure divided by the number of moles total, which reappears in every one of these terms. And so here I've regrouped these. I now have the pressure divided by the number of moles total raised to the power of minus 0.5, and here just n, the number of moles. Now for each of these things, in the table, for instance, I know the number of moles of SO3 is equal to Y. The number of moles of SO2 is equal to 1 minus Y, and the number of moles of O2 is equal to 1 minus 0.5 times Y. The pressure, I was already told, is 2 atmospheres, and the number of moles total is equal to 4 minus 0.5 times Y. So if I substitute each of these into this equation, then I have one equation. 1.8 is equal to this expression and one unknown, just Y, which means with this equation I can solve it and I can get a value for Y. Okay, so that's how you get started on this problem. Don't forget, just as a note, that you were given this equilibrium constant in the problem and it's specific to this temperature of 1000 Kelvin. If you were given this constant but not at the temperature you need, don't forget that you can use the Van 't Hoff equation to adjust this equilibrium constant to other temperatures. So what happens to all of that sulfur? If you look, actually, sulfur is produced in really large quantities, and if you look at the list of chemicals that are produced in the highest amounts, the number one chemical by far is sulfuric acid, and it's been that way for over 100 years. The reason for this is that it's an important chemical for a lot of industries, and especially it's used for producing fertilizers. Sulfuric acid has also been increasing over time. So have fun solving the problem, and I'll see you in class.